So we're now looking at another hypothesis, joint hypothesis, and this joint hypothesis is that several of the betas are all equal. So this hypothesis is most common with indicator variables, and so it's useful, for example, all products are equally successful, or all neighborhoods in Waterloo are equally expensive, or something like that. Want to make one technical point here. The F-test only applies to nested models. The hypothesis that we're proposing here imposes a restriction on the unrestricted model. And a restricted model is always nested in an unrestricted model. To give you an example when this is not the case, here I have two models, one with x1 and x2 and the third one with x3. You can still compute the difference in sums of squares, residual sums of squares for these two models, but you can't use an F-test to evaluate whether one is significantly larger than the other. All right, so to test this hypothesis of equality, we need the full model and we need the reduced or restricted model that results from applying the hypothesis to the full model. And we'll look at one specific example. This is the Kitchener-Waterloo housing data, which contains list prices of houses and attributes of the houses. And we'll look at the hypothesis after adjusting for square footage. All neighborhoods in Waterloo, but not Kitchener, are equally expensive. So there are houses in Waterloo and in Kitchener in this data set. So the hypothesis is there's 10 betas corresponding to neighborhoods in Waterloo, indicators, and they're all equal. Here's some output, R output. You see whether they're in Kitchener or Waterloo is indicated by a W or a K in here. There are 11 Waterloo neighborhoods, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And so I'm going to offer some more explanations. As before, we have put the list price in units of $100,000. That has nothing to do with computations. It's all about the coefficients. Large coefficients are just harder to look at, so I wanted them to be small. So price 5 means house costs $500,000. The houses in downtown Kitchener, so neighborhood downtown, were used as the baseline neighborhood. And for some houses, neighborhood was not available in the listing that we looked at. And so those have been grouped into a neighborhood called unavailable. And some neighborhoods, there was only a single house, and those have been grouped into a neighborhood called other. This is a little aside, not to do with this problem. If you have an indicator variable for a neighborhood and there's only a single house in it in your sample, then you can compute the effect, the price increase or decrease in this neighborhood, but it's only based on a single observation, so it's not very reliable. But also it doesn't help you much because it uses up 1 degree of freedom. It's one observation. You have to estimate one parameter for that neighborhood. And you don't get any idea of the variability because you only have one observation. So that's why I made the choice to combine those into a neighborhood other. Here I have the model in data with neighborhoods combined, regressing price on floor space, and the indicator variables here. And so for the Waterloo neighborhoods, they're all combined into a single indicator variable. Now, so what that means is before we had 11 Waterloo neighborhoods, and now we have an indicator. So the difference is 10 in parameters. Here is the same thing for the R code. It's the same. It's just an explanation of how to do the computation is slightly different here. Okay, so we have to conduct the F-test. The F-test is the difference between the reduced sums of squares error and the full sums of squares errors. We get that from the model. And we divide by 10 because before we had 11 parameters for the neighborhood Waterloo. And now we have one parameter for the neighborhood in Waterloo. And so we have removed 10 parameters, so 10 degrees of freedom. And from the full model, we get the estimate of sigma squared, and that turns out to be 1.007. Now we know what we're really trying to see is that reduced model, does that lead to, well, this estimate of sigma squared much larger than that one down there? And 1.007 certainly is not much larger than 1. So we think, well, probably nothing here. And it's true. The probability of the F value exceeding 1.007 is actually pretty high. It's darn close to 50%. So the probability that we observe an F value is small. Yeah, I just said that. Therefore, because it's not significant, we fail to reject that the neighborhood and Waterloo have different prices conditional on floor space, because floor space was in the model. So the conclusion is we combine all Waterloo neighborhoods and just keep a single indicator for that in the model. I want to clarify one thing. This does not mean that all Waterloo neighborhoods are actually equally expensive. It is probably true that there are several neighborhoods in Waterloo that are more expensive than others. But in this sample, we had a relatively small sample size, 94 maybe, and spread over a large number of neighborhoods, both in Kitchener and Waterloo. So you think there's probably only 40, 50 observations in Waterloo spread across these 10 neighborhoods. So the sample size is small. So in these data, there is no evidence that the price is different. And just from a data perspective, we can combine these indicator variables into a single one, but that doesn't mean we could do the same thing if the sample size were larger. And actually, it wouldn't be. It's just that the sample size is small. All right, with that thought, I leave you for another day.